In this course, we will discuss various engineering parameters of antennas. We will also further discuss the uh, various types of antennas, which include wire antennas, arrays of antennas where multiple antennas are grouped together, and a special variety of antennas which are called aperture antennas, which appear in microwave frequencies. One of the parameters, engineering parameters of antennas is antenna impedance. When an antenna is connected to fed by a transmission line, it offers certain impedance, which is important for us to understand. The radiation resistance is the resistive part of the antenna impedance, which indicates uh, the amount of real power which is transferred from the source in form of radiations. Since this amount of power is not going to come back to the source, it is a loss to the source. So, in that sense, the amount of uh, radiated power is indicated by imagining that antenna has a virtual resistance, which we call as radiation resistance. In addition, the antenna physically has certain resistance. As current is flowing through this loss resistance, then uh, the antenna gets heated up, some amount of real power is dissipated. So the loss resistance of the antenna is indicative of actual loss, because the amount of power lost in the antenna loss resistance is a loss to the source. Accordingly, we have a uh, term for antenna efficiency, which is basically the radiation resistance by the total resistance, uh, as often expressed as a percentage. The impedance of the antenna, the real part, will take as the radiation and the loss resistance put together. Usually, the antenna has got some reactive component uh, that could be inductive or resistive. For example, if the dipole is exactly halfway long, then uh, typically the resistance would be about 73 ohms, assuming it has no loss, and it has an inductive reactance about 42.5 ohms. And if you slightly reduce the length of this lambda by 2 dipole to about 0.48 lambda, then impedance reduces, but important part is it becomes a resonant length, and the resistance, the antenna appears as a pure resistance with reactance cancelling out. And if you reduce the length even further, then it appears as a capacitive reactance. Antenna polarization. So you know about wave polarization. Uh, Antenna polarization is also similar. So we say antenna is, let's say, linear polarized. Its meaning is that the radiated EM wave from this antenna is linearly polarized. Similarly, the uh, circular polarized antenna is producing a wave which is circular polarized, and if the wave radiated is elliptically polarized, then we call it as elliptically polarized antenna. So, in short, we say antenna polarization is the polarization of the wave radiated by the antenna. Then, as the most analyzed part of antenna behavior, we have radiation patterns. All antennas radiate differently in different directions. The the parameter we measure or we assess in various directions is the magnitude of electric field, how it varies in various directions, theta direction and phi direction. To assess how this directional nature of antenna radiation is, we use power pattern. So we define a parameter called radiated power density, the amount of power which is flowing per unit normal area away from the antenna, and we assess in 3 dimensions how it varies as theta and phi vary. Since this radiated power also changes with distance, we assess this at a fixed distance. A more convenient parameter is radiation intensity. This is independent of the distance from the antenna. The amount of power radiated per unit solid angle in a given direction, because of